Okay. Do you see my slide now?
Yes, it's clear now.
Okay. Let me close it a little bit. So good afternoon or good evening, everyone. Thank you for staying here until this time. I will not present you quite long presentation, but I will try to keep it as short as possible. So this presentation paper is about one of the sub area of the bigger projects called Explainable Cyber-Physical Systems. That is a real cooperation project between Vienna University of Technology and then Siemens Austria. And for this part, we cover a smaller components of the system that is for defining, building the explainable cyber-physical systems, more especially for the causality part. I will tell you a bit later about the details, but for now, I will introduce you a little bit about the concept of the explainable cyber-physical system. So basically, what we have, what we want to achieve is that in the future, cyber-physical systems, which are actually a complex system by itself, which has some actuation and then some sensors, and also integrates various data, and then it can produce a different behaviors. For example, in our case, we have an example, a power grid, or in the future, it will be called smart grid. And then, for example, there is some events that happening in the grid that will probably a disturbance. And then we would like to know the reason, for example, for such events happening. The usual approach is that we contact some customer service to ask about what's happening, and then probably they cannot really help. And then we also need to do ask about the details, probably the technical details, but we will try to somehow automate this process by encoding the knowledge necessary, and then try to extract the explanation from the integrated knowledge. For further discussion about these explainable cyber-physical systems, you can refer to the previous publications in the modeling and simulation of cyber-physical system workshops. So, for example, here we have and in a particular smart grid situation where people have a charging station charging their electric vehicle, somehow getting notification that the current is reduced due to some command from central algorithm. And then they would like to know why this thing can happen. So basically, by you tracing the events that is happening on the cyber physical system, we can hopefully automate this generation of explanation. For example, this pole capacity is reduced due to the limited grid capacity or based on tariff. For example, the grid is currently overloaded by the high consumption. And this was due to some of the part of the community that is usually taking self-sustained power from the power photovoltaic system, suddenly try to take the power from the grid, because then the weather is not good. So here we try to construct an explanation, because the weather has changed, then the higher consumption is happening, and then the grid is limited, and then the charging station takes the blame to get the reduced load. So this is illustrating scenario about what is an explainable cyber physical system is. And basically what happening during the explanation generation is that we have a system which is a static one, and then containing the topology of the components and how they're connected to each other. And we have from our side, we have an initial context knowledge graph, which is containing additional knowledge about the system. here we combine this is actually the causality relationship between the components. And from the system, we can also receive the dynamic information, for example, the states used in the terms of event log or time series. And from this, we also have the events that is annotated, for example, and from the time series, it is summarized into some events that are happening, like overload or high consumption. And from these two knowledge, then we have integrated into a new knowledge graph called the event causality, containing the events and then causality. Then we use this to generate, try to construct an explanation for the events. And for this big topic, I will cover for this presentation only on the causality part of the system. So we would like to represent the knowledge regarding the causality that will be helpful to construct an explanation. Regarding the causality representation, there are so many methods to represent causality. We look at as in the literatures, and we somehow arrange it into some categories. For example, the first one would be the free text causality, then that is including or having the relation, a temporal relation, but this would be needs some kind of NLP techniques to extract such things. And we also have some semi-structured functional model. In sometimes it becomes a tabular, like the failure mode or mode effect and analysis, and also fault tree analysis in the tree structure. And then we have some ontology-based representation called event model, and then we go so on and on using a very specific model, and then going abstract more into some algebraic. So here is the situation of a different way people represent some causality. So on one end, we have a very expressive way to express the causality using a free text, but it requires further techniques to extract this. And the other end, we have a very abstract representation in form of variables, and which has no meaning. We still need some additional meaning. So what we want to achieve is that we want to be around, we have a very precise meaning of what the variables are, what it represents in the real world. So we will go to this apart. Looking into the semantics approach, here is the ontology of our explainable cyberphysical system. So it's basically we have the cyberphysical system represented at the group at the top. We have the feature of interest are things in the real world. They have some properties like physical properties, which then observe or interacted via device, and then they will generate the data. From this data, then we can annotate some events. And from this event, we would like to construct an explanation using the information knowledge from a causality that is a relationship between the property. I will go into details with this causality between properties. So basically, causality is just a cause and effect relations between two things. And in this context, it would be a property A influencing the property B, probably with some conditions. So in this case, for example, solar intensity influencing the power generated in the photovoltaic or solar panels. Also, power can also influence power. In this case, the solar panel will reduce the power consumption at the house, and so on. And what we want to achieve is the causation part. The event is caused, event A at the particular location is caused by event B at the particular location. But so the question would be in this paper would be how exactly to represent this condition part. This would be, we have the data now in the knowledge graph, and then there can be many ways to express this kind of constraining condition. Therefore, we choose SPARQL, a query language to to formulate this condition. So we form this in this schema. Causality condition is formulated using SPARQL. What it looks like is here. For example, this data is formulated serialized using RDF. And in this RDF, we have two entities. The first one is the causality between the active power and then the load of the transformer. And these only happen, we specify more restrictions about this relationship, because the active power is measured not just in, for example, in the building, but also in transformer. And then the loading is not just only in the transformer, but also from the cables, distribution cables that are in the grid. And therefore, we specify these using some pattern. For example, the first one would be this was a device placed at some features, and some features needs to be connected to the target features. In this example, there would be some cable connections. And the features of the source would be the power grid connector or smart meter, and then the target would be the feature is a transformer. Here is the so we have the data first. In order to get the causality from the devices, we first query the data devices that are measuring these two properties, and then we query again the data that will return the pair of the device that is source and target that fulfill the constraints, and we do some intersection of this one. Once we have, for example, this causality, then we have the causal relationship between the devices. For this example, I will show you a bit in the scenario. For example, here some schema of the grid that is we use for an example. In the center would be the transformer, on the left would be some commercial buildings and then charging stations. On the right, there are some residential building, and we have some also data grid layer where some residential are participating in flexibility scenario, which is a demand. Some can change their demands through a communication with the server. And here some example explanation. For example, the E7 or the trafo overload, they are increased because of the preceding events, that is E456. Those E456 are increased in consumption. The E4 and 5 is because they have a notification from the flexibility server that they can increase their consumption. But for the E1, the E6, it is an unexpected, because they usually have the power stored in the battery, but because they are not charging, the weather is not good, then they consume more and increase the load to the transformer. That's the example explanation. So here is what it is implemented using the Bifrost. The Bifrost is a simulation platform made by Siemens, so to simulate this power grid. This is the something like represent what we previously described. We have the transformer on the left, and we have some residential house, and then the building and the charging station. If you this is already showing the explanation generated during for the transformer. For example, here on the top right, you see that the overload event at 10:30 is happening, and this is caused by the peak consumption at the EV station, residential, single, and commercial factory. And also each sub of the events, they also have their own explanations. For example, the peak consumption at residential single is because of the flex request, or they due to the low solar output in the solar panel and low solar intensity measured in the global sensors. Here is the serialization of what exactly called the event graphs, like, and so yeah, the event graph contains more detailed information, and this top one is the simplified for easier consumption for some users. How it works is actually first the causality we conform into a knowledge graph. For example, here you see we have some properties here, like the weather influencing the solar panel. Solar intensity can influence the generated power, and then this will influence the load level of the transformer, and so on. The other also do the same. Here is the abstract level, the something that we know, and then we going into a more concrete example where each properties are here is we only involve the sensors, like the solar intensity is measured by intensity sensor, and then loading have there some meter, we have smart meter, and then the charging actuator. And then they are placed in a real situation where the real objects, like for example, the intensity is placed on the PV system, and then the load level is placed at the transformer and the smart meter in the building, and they have some topological connection to each other through power line or some other mediums. And if there's events happening, for example, in the building, then they will follow this path through the N event, and then they will become an explanation for an event. So that's for the presentation. As for conclusion is that in order to generate the explanation in this CPS, we exploit some causality knowledge that needs to be represented, and we use it a rule with additional constraints to derive the more concrete rules. And we use this SPARQL-based causality in the context of knowledge graph-based explainable CPS. For now, the rules are manually crafted by the experts, but we were looking for the next thing is how to automatically extract this causality relation from data, either from example by the experts or a time series data of the previous simulation or previous measurements. And the current rule of the causality is basically deterministic, and we don't have any way to this determines which explanation should be put first. So the next thing would be in the work is actually defining the weight scoring scheme in order to get some ordering on the explanations. I think that would be all from my presentation. If you have any questions, please. Thank you.
Thank you. Any questions from the audience? So it's the final one. Okay, a short question from me. Can you explain the benefits of using SPARQL for this? Besides that, the target that you mentioned that you want to explain, you want to put in the middle. But what's the benefit and also the drawback, the fitness of this SPARQL for?
So in order to get this a path from one event to another, we need to follow this path. And then what we already know is, for example, in the abstract causality, like we know that weather is connected to the PV system. I mean, the solar intensity will influence the power generated at the solar panel. But we have, this is just the abstract. It's independent on whether the configuration of the system is. And then we have the configuration, actual configuration of the system that has these devices placed at particular place, but we don't know exactly which combination, which pairs of the devices that are having this causal relationship. And this causal relationship therefore expressed as a constraint using the SPARQL. And using the graph of this system, we can use the SPARQL as a graph query language to express exactly how the constraints should be fulfilled, the conditions. That's the benefit of using the SPARQL. So we don't have to manually annotate the causal relationship for every pair of device. So it's reduced the work of the experts in this case.
Okay, thank you for the explanation, and also thank you for the nice presentation and discussion.